My dear students, session started the approximate method called cantilever method, and we have seen the procedure also, and the assumptions in cantilever method. So just to recall once again that the cantilever method has got two assumptions. Is the each and every member in the frame will have a point of contraflexure at the center of the member, the middle of the member. Second assumption is much important, where you the differentiation of the method uh, is based on that only. So second assumption is like uh, the very particular to this cantilever method when compared to portal method. So in portal method, we related the column shear in interior column to column shear in exterior column. Whereas in cantilever method, it is to relate the axial stress in column to its location from CG of all the columns in that particular story. So axial stress in other sense, it is like axial load. Okay, right. So this is the solution. As the assumption is column axial stress, so intern axial load. So we start our procedure with column axial load. So step starts with the calculation of column axial load. So once you know column axial load, then we will calculate the connecting quantity beam shear. Then we calculate once you know beam shear, we calculate beam end moments. So once you know end moments, we will calculate column end moments. So after column end moments, we will come to column shear, and that will be the last step of calculation. Right, we started step one for this example that is taken from 2017 October. So we apply first assumption, and this is looks like this. So first assumption says each member will have a point of contraflexure at the midpoint of that member, right? So after that, going for the second assumption, so it says the column axial stress is proportional to the distance of that column from CG line of all the columns. So first you have to work out CG of all the columns. Then only you can measure this X. See, without knowing this line, this CG line, you can't get this distance. You can't get this column distance. Likewise, you can't estimate the X distance of particular column without knowing this line where it is. So first locate CG of columns. That's very simple. So you just recall your CG formula from your mechanics part. So x bar is a1 x1 plus a2 x2 plus a3 x3 and so on. We write these many number of terms. The reason why you have four number of columns. Okay. So as you have four columns, you include four terms in numerator and denominator. Right. A1 means cross-sectional area of column 1. Okay, so as the distance from a reference line to column 1 is 0 because the column 1 itself is taken as reference line. Okay, you remember from mechanics that to calculate x bar or y bar value, you need a reference line. First, you choose a reference line, then you work out x bar and y bar value. That will give you the location of CG. So that is to recall from mechanics, right? So this is now the reference line. This line is reference line. Okay, this one vertical line where the first column exists. So x1 means distance of column from reference line. So column and reference line at same location. So distance is 0. Hence everything is 0. Then A to x2. So capital A cross sectional area of column 2. So as there is nothing mentioned about column cross sections in the problem, I am considering it as assuming it as same, that is, and x2, the distance of that column 2 from CG line. Okay, from reference line, sorry. So we are working out for CG line. So from reference line, what is second column distance? This is 3 meters. Okay, right? So until you calculate x bar value, all your distances are from reference line only. Okay, so x2 3 meters, x3 from reference line, third column distance 4 plus 3, x4 from reference line, fourth column distance 3 plus 4 plus 5, 12, and the denominator is like a1 plus a2 plus a3 plus a4, sum of all the areas, it's 4a. So 5.5 is the CG location. Okay, so it is just a recall, and after calculating now CG, uh, this cities that looks like this. Now these arrows are to be mentioned by you, and I told last session these arrows have come. So CG line to the left hand side, downward arrows, from CG line to the right hand side, upwards. Reason, resisting direction should be opposite to the applied direction. Right, so this is the location where this load is trying to rotate this frame about that clockwise direction. So you need an anti-clockwise moment. So that's why the downward arrow to the left, up arrow to the right create anti-clockwise moment. So likewise, so all the left side columns, left hand side columns from CG line will be downward, and side columns of to the CG line will be upwards. So that's how we work out the directions. Okay, so next is to apply theorem assumption. So what is assumption? Stress means the area. Say this is the first column, AH by area, sigma divided x distance of CG. So sigma x is equal to some k constant that now is don't that k. Okay, so just it's in the right is equal to the second FPG sigma BG by distance of this column from CG to the other columns. You write the relation, then you try represent all the axial in terms of particular column axial load. So selected the first column. So column axial or column axial load. This is how you see. So there is a relation between every column axial load. First one, BG2 first column, I mean second column is this, CF2 column, and then DE2 first column. Likewise, the column axial loads present in that story are related to any one of the column. You choose last one. Likewise, you choose any of the columns. Okay, right. Now you choose equation because you have four unknowns. You see, there are four columns, four unknown axial. So you have three relations possible from assumption 2. So the other one should come from the existing relation that moment at point of contraflexure is 0. That you have to take. That's it. So choose the point you have selected the column for relating other three, the same column you choose, and then take moments. So that will give you an equation in terms of other three axial loads. You have already relations with the first column. So substitute them into this equation. That will give you the chosen column axial load. Then substitute back all these the value that you got into all these equations will give you the other three force axial loads, other three axial loads. Okay, so that's how we have completed step for story. Right, let's move to the second step. Okay, so I have taken a section. Let us see how this is represented in the diagram first. Okay, then we do second story. Say 3.39544 and 4.0. Remember, these are downward arrows and these are upward arrows. Let's see how it is being represented in the diagram. You see, so look for only this half of the diagram that you have taken. So downward 3.394, downward 1.544, up 0.927, up 4.012. So what you do Remaining half, just put an opposite arrow, that's all. If it is downward, you put an upward arrow. If it is upward, you put a downward arrow. So that completes the first story column axial load representation. Okay, got it? Right. Okay, so you still don't know these values. Okay, so that we will work out. Right. So now you pass a section through this story number 2, story number 1, story number 2, and take this part free body diagram. Okay, got it? So you have 20 kilonewton as well as 30 kilonewton also coming into picture. Right, see this? So this 5 meters and the next story is actually 4 meters of full height. So we cut at middle. So it is only just 2 meters left. Right, again you do the same. So first apply assumption 2. So sigma hi by the distance, same 0.5. So no change. Columns are not changed positions. Column positions are not changed. So denominators will not change. 5.5, 2.5, whatever is used earlier in the equation, same, except you change these column notations. That's it. F, K, E, L, all that. And now you relate each one to first axial load. That means second column axial load is equal to some constant into first column axial load. Something like that. Third column axial load is equal to constant into first column axial load. Right. So similarly this one EL also. Okay. So you have got again the same relation with the different numbers. Okay. So that's how it is. 0.455 and 0.273. Nothing has changed. You can see I'll show you the same values earlier also. Okay. So here you see 0.455, 0.273, 1.182. Only change is the notations, that's it. So column notations have been changed. Gj to Hi, Fk to Hi, and El to Hi we have related. That's it. Now what is a change then? Here is a change. Taking moments about this point. So you take moments about this point. So 20 is a clockwise moment. 20 into this distance. 5 plus 2, 7 meters. Then 30 into this distance, 2 meters. Then anyhow, Fi into distance is 0. This is a moment center lying on this line. And then this one into distance is 3. Okay, Fgj. Then this one anti-clockwise. Distance, this one 4 plus 3, 7. This is 3 and this is 4. Similarly, this one is also anti-clockwise. So minus, both are up. These two are opposite in nature. You see, 20 is clockwise, moment from 20 clockwise, moment from 30 clockwise, moment from GJ clockwise. So these two are anti-clockwise. So minus. Now what? You have relation between GJ to HI. Substitute that. What is FGJ? You substitute 0.455 HI. What is FK? You substitute 0.273 hi. What is EL? You substitute. Okay. Then what is the unknown remaining here is just FHI, first column axial load, 13.58. Then substitute this into all these three relations. Substitute for HI here, you get GJ value. Substitute for HI here, you get FK value. Substitute for HI here, you get EL value. So that is second story column axial loads. Okay. So that is 13, 13, 16 CG, CG, CG. Let's see how it is. You see it here. So where we have worked out this. Okay. So 6.17, 16. Now what you need just to place an opposite arrow. Uh, representation. Okay. That if you upper part, you are getting those directions. If you choose the low, you get these directions which are now just mentioned depending above direction. So these arrows you will be getting the section. And you are not taking it because you have a fixity here. Fixity here. So fixity at the bottom, and you have three reactions there again. So it is again increasing of unknowns. So a bit more is to be done. Equations are to be generated. That's why comfortable with the portion above the section. Okay, right. Now to work out the first story, bottom story. Okay, so pass a section bottommost story midpoint through the middle. Okay, through this. Then consider the whole part above that line. Okay, so now you have this is 1.5, half of 3. So that is now taken for workout. So 1.5, 5 is anyhow 3, 4, 5. Okay, right. Again, we start with this relations sigma by nothing is changed. Same distances, column distances are same. CG no change because this column is never CG line. From CG line, AH, HI and IP are all at same distance 5.5. Same 2.5, 1.5, 6.5. So no change in the relations. Only the names will change. Okay. Right. And then next taking the moment about the midpoint of the first column is the same here. And now write the moments. So 20 into the distance, perpendicular distance. 5 plus 4 plus 1.5, 10.5. Then 30 into 4 plus 1.5. Then 40 into 1.5. Then JO into distance 3, then kn fkn into 4 plus 3, opposite you see, same here, lm into 3 plus 4 plus 5, 12. Now substitute for what is jo and ip relation, kn and ip relation, lm and ip relation from the previous relations. All these, these three relations you substitute in that equation. So you get FIP value. Then substitute back into those three relations, you will get all these values. And then you represent them in the diagram. So this is where we worked out. And now you just put the opposite arrows. Okay. So this completes step. Okay. So you are working out half of the story, and then you are producing the other half, other part of free body diagram. If you work out, you could have got the solution. So this is how the axial loads are. Okay, right, you see. So out of all the LM has got 34.912, the maximum axial load. Okay. Right. So remember, first work out CG location, then formulate the relations from the second assumption, that is sigma by x is equal to some constant. Then use those relations into an equation, moment equation, where moment is 0 at the middle of a member is used here. Then we solve for 4 axial loads. Likewise, each story you have to take, then complete all the stories, then represent all these values with their counterpart arrows also. Okay, for equilibrium, right? So that's the end of step 1. Okay, this step very lengthy one, but very similar workouts for right from story 1, 2, 3. Okay, all these now will have very similar relations, only just the steps are a bit lengthy, but to work out it is very easy, right? So next session we will see the other steps like 2, 3, 4, 5, which are much simple than this, because once you know solve this one, all other are just connecting quantities, right? Thank you.